Start recording. There we go. Since the energy is conserved, which is the first law of thermodynamics, statements 1 and 2 are true and statement 3 is false. Okay, so that's the answer. It says, which of the following are true in relation to thermodynamic changes? Is it number 1? A system undergoing an exothermic change will release energy. Are we all good with that? That's just a definition. Exothermic reactions release energy. Number 2, the surroundings are absorbing energy. Hopefully, if you recall, the system is whatever you're looking at, the reaction, and then the surroundings is everything else around it. So this is like the reaction. And if the system is giving off energy, then the surroundings must be absorbing that energy. Does that make sense? Does it make sense? Yes, good, thank you. Why is my finger writing? Oh, dear God. Okay, that's not good. Okay. No. Okay, I'm going to close this and open it again because I can't have my fingers writing. They need to be able to move things. There we go. Okay. And number 3, a system going an endothermic change will absorb more energy than the surroundings release. So if it is true, if this statement is true, where's my little doodad? There it is. There's my eraser. Here is the system absorbing energy. And here is the surroundings releasing energy. Is it possible for the system to absorb more than the surroundings release? No, because where would that extra energy come from, right? It's just like it doesn't come from anywhere. So that's why number 3 is false. It's a bit of a tricky wording question. I feel that's maybe what caused that issue. Oh my God. Okay, it's fine. Page down. There we go. Okay. Number 7, honestly, I don't think AP gives a rat's behind if you know what a state function is or not. They never ask about it, okay? University will care. You should know that enthalpy is a state function. I don't think we care about density because whatever. And you should know that heat is not a state function. If you are interested in reading about it and why this is the case, there's a little thing you can read about, but we're not going to talk about that because it is not important to the AP exam. Okay, so we're just going to keep going. Number 11, if energy cannot be created nor destroyed, it must stay within the universe and therefore cannot leave or be introduced. So we are being asked, when considering the first law of thermodynamics, the universe is considered to be a closed system, an open system, part of the system, part of the surroundings, sometimes closed, sometimes open. Basically, the universe, as far as we know, doesn't have anything outside of it, so nothing can leave and nothing can enter, so it would be a closed system. Yes? As far as we know. Yes? Why is it not a part of the surroundings? Because it is the whole universe includes the system. Yeah? Universe, system, surroundings, and the universe is everything. Yes? Energy can leave a closed system. I don't really like this question for that reason. I was like hoping that no one would notice that because I just wanted to skim over it because it's not a good question. Yeah? But you're absolutely correct. Energy can leave a closed system. This should be called an isolated system instead of a closed system, I think. Isolated does not transfer energy either. Okay. Sorry, we're going to have grumpy face on me when it won't move when I use my fingers. All right. Number 13, a term that is only associated with a decrease in enthalpy. So an exothermic reaction. What does an exothermic graph look like? It starts low or high? Starts high and finishes low. Okay, so is that a decrease in enthalpy? Yes, because this is potential energy, which we can think of as enthalpy, even though enthalpy isn't really potential energy, but it is useful to think of it that way. Okay, so that is exothermic. So this is correct. Obviously, if that one is correct, then B cannot be correct. Yes, because this would be an endo. What's wrong with me? That's supposed to be a triangle there. Didn't work very well. Okay, so obviously endothermic reaction is incorrect. Enthalpy change. Which of the following is associated with a decrease in enthalpy? Well, that's just a silly answer because an enthalpy change could be positive or it could be negative, so it's not an enthalpy change because it could go either way. Heat of reaction, again, that's something that could be positive or it could be negative, so it's not necessarily a decrease in enthalpy. And we're asking about enthalpy, so what does that have to do with entropy? The two they work together to drive reactions either all the way to completion or forming equilibrium, or they say to the reaction, stop, go no further, but they don't affect one another, like they're separate entities, okay? Alrighty, that was 13, and then we have, yeah, for sure. Number 16, in a reaction where the potential energy of the reactants is lower than the potential energy of the products, which of the following is true? Is the reaction endothermic? So the reactants are lower than the products. Is that endothermic? Yes. Does that have a negative delta H? No, because delta H, we are starting low and finishing high. So that is no. And the only one that's a little more complicated is the bond energy of the reactants has a larger magnitude than the bond energy of the product. So if we have Can I not move this thing? Do I have a picture here? I do. Okay, so here's our picture. So if we have bond energy of the reactants, now if I have reactants, let's say I have, this is actually a question from later on. If I have hydrogen and fluorine, and those two are going to react together to give us HF. You need to know that bond breaking, is that endothermic or is that exothermic? If you break a bond, it is endothermic. And if you have trouble remembering that, I want you to imagine that you have a stick, okay? Do you need to put in energy to break that stick? Yes, and you are breaking bonds. Therefore, bond breaking is endothermic. You must put in energy. Does that make sense? Okay. So that means if you have to put in energy, that means that delta H is positive. So we have here breaking these bonds, that's a positive delta H. And if we are told that the energy of the reactants has a larger magnitude, so this is big, the bond energy of the products, delta H, is going to be negative. And that's because when a bond comes together, if you've got, like, say, hydrogen here and hydrogen here, yes, and in the center of each of those, you have a positive nucleus. I don't know why I drew an H. I really wanted to draw a positive. These little electrons, what do they want to be close to? The little electrons are negative. What do they want to be close to? They want to be close to the positive. So, how can we get them close to more positive charges? We can if we put them together, now instead of being close to one nucleus, they are close to two nuclei. So that means that's going to be a more stable arrangement for those electrons. And when things become more stable, what's happening to the potential energy? It's getting lower, okay? And so that's why bond formation is exothermic, because the potential energy is getting lower. And so this is releasing energy to the environment. So that is exothermic. And so this is going to be a negative delta H. And this is, we're told by the question that the reactants' bond energy are bigger than the products. So this is smaller. So we have a bigger positive number and a smaller positive number. So that means that overall, if we take the two of those together, overall, that is going to be a positive number. Yes? I need my gloves so I'm not writing like a 3-year-old. There we go. Okay. Okay. Yes.
On the top, you put like a touch thing.
Where?
On the top left.
Top left.
You do that.
Oh, bless you. Okay. Oh my God. Olivia, you have made my day. Anything you need is yours. I owe you. Okay, fantastic. Otherwise, it was going to be grumpy face all day long. Oh my gosh. All right. So do we feel okay about that one? I think number 3 said, if the bond energy of the reactants has a larger energy than the bond energy of the products, that means it is overall positive, which means it is overall endothermic. Nope, didn't fix it. I don't know. Why is it doing that now? More space between opposite, what? Oh, I don't know. It's still doing it, but only intermittently. I don't know. See? I'll ask Mr. H. Maybe he'll fix it. Maybe I just need to shut my computer down and start it up again. Sometimes that works. Okay, at any rate, we have an endothermic reaction, and this was number 3 also gave us an endothermic reaction, so that is true. Yes. Yeah. So for all endothermic reactions, the bond energy of the reactants will be bigger than the bond energy of the products. Is that correct? Yes. Yes. All right. And that's it. That's all we're going to do on those for today. All right. And we are now going to go to our AP Extras. All right. Oh, did you have any questions from the homework? Anyone? Other than the fact that I gave you the wrong number. It said page 6, number 3, and it should have been page 3, number 6. Okay, good. Now, first things first, your cover page, the It went out to print before I realized that the numbers were wrong on the very front. So 2.5, the page number should be 84 and 89, and then 94, 99, 105. So if you want to make that correction, you can do that. That's on your cover page. So that's the equilibrium and thermodynamics section. Yeah. Sorry about that. Okay. And now we are going to go to, oh, not that one. We're going to go to 1.7b, which is on page 57, 57.
So much fun.
Yes.
Is this book the AP Chem materials book?
This is the AP Chem material.
And then
So
the other one.
the other one is the regular stuff. And for the first part of the regular stuff, it is just a little bit of review of Chem 11, like its unit conversions and moles and things like that. The only thing is you're doing a rate, but that just means put the moles over the time and practice doing some conversions. So we're going to be focusing on this for now. You guys are going to be learning the reaction kinetic stuff on your own just for the start, and then we're going to get into it together. Okay? Yeah. All right, so we're going to watch a little video on absorbance and transmission spectra. Okay. And don't forget, which one has the smaller wavelength, red or purple? Smaller wavelength. Purple, okay? And that means, is its frequency high or low? Purple's frequency is high, okay? And you can see that in the diagram because we've got 400 nanometers, that's our purples and blues and stuff like that. And over here, 700 nanometers is the reds. And yearbook sport. Yeah. Okay. Amy, it's for you. Yeah, it's last year's yearbook. No, it's this year's yearbook. It just traveled in time back to Amy. No. Okay. You, as a university level chemist, would only be doing visible light spectroscopy. Yes? Later on, if you go on to pursue more chemistry things, perhaps you'll get into those more exciting gamma ray things and whatnot. Does that make sense? So we got this red thing, it absorbs everything except for red. The red comes through and we're like, oh, look, it's red. And unfortunately, your book is in black and white, so I did write out the Roy G. Biv, and then all the absorbed light is the Oi G. Biv, okay? Okay, so if you look at a solution and it is yellow, what light is it absorbing? It's absorbing violet. Okay, so what if a solution looks green? What's it absorbing? Red. So you don't need to memorize the nanometers here, but if you can, like let's say you're on the AP exam and they're like, you have a blue solution, what color is it absorbing? If you can just draw something like this, right? And it doesn't even really matter which direction you go, whether you go red, orange, yellow, green, blue, indigo, violet, or you go the other way around, red, orange, yellow, green, blue, violet. Then you can say, oh, my solution is yellow, it's absorbing violet. You just look across. So that's a nice little, you look puzzled, Tony.
Also, it says 560 nanometers.
And it says what?
It says 400.
Oh, I don't know. I mean, yeah, this one, I don't know what this guy's done. 450 to 480. That should probably say 480 to 560 for green. Yeah, but I don't control this video, so there we go. Like I said, you don't need to memorize the actual wavelengths. You should know that visible light runs from about 400 up to about 700, so like 4 to 7. Yes? Is the, which on the graph? Yesterday's graph, yes.
So instead of like,
Yes.
like this and
Yeah. That's what this is talking about. So on that graph that we saw yesterday,
oh, that's my
on the graph that we saw yesterday, let me just grab this and maybe draw on the side here. You had a spectrum that looked like this or something, right? Okay, it had a peak. It may have two peaks, but it's got one peak. So if this was our red ruby, okay, let's say we managed to jam that into our spectrophotometer. Red is opposite of green. And so, and green is from 570 to 495. So we would expect that to be, I don't know, maybe 550, 530, something like that, right? It would be, you know, this here would be like somewhere between, what did I say? 495 to 570. So that is absorbing green. It absorbs green the most, and so it appears red. Is good? So if you have a blue solution, you know that you are going to be selecting, can I make it bigger? Yeah, so if you have a blue solution, it's going to be absorbing orange. And so you would start looking at your wavelengths between 590 and 620. So you don't have to go through the entire range. You might go a little bit outside of that as well. But those are the wavelengths you would look at when you are plotting your absorbance versus wavelength graph. Did that make sense? Yeah? Okay. Cool, cool. All right. So you would either tilt the prism so that the rainbow moves up and down, right? And then the slit stays in place, or you would move the slit up and down so that instead of, let's say, hey, there it is. So you could either tilt this so that the rainbow then, started here and finished here. And so then you'd have purple going through. Yeah. Or you could move the slit up and down so that instead of, if we move the little hole in the slit up to there, then the red would go through. Does that make sense? Miss Erin would like to see you about some course thing. Okay. All right, so let's go back to our little video here. Do you guys remember the logarithmic relationship? How would you calculate absorbance given the transmission? You would take the negative log. Okay, yeah.
Oh, yeah.
So this comes in handy when we're doing reaction rates, because one of the things you can do to measure rate of reaction is you can look at the concentration of a colored species. Like you can pour your reaction mixture together and then toss it in the machine here, and you can read the absorbance as time goes on. You can read the absorbance at time 0, at time 5 seconds, 10 seconds, and you can see the color either increasing or decreasing as time goes on. And then you can plot that and get a reaction rate graph. So this is a beautiful way of finding the reaction rate if you have a colored species. If you don't have a colored species, though, useless. Yes? Because it just won't work. Why would you choose that one? Why do you choose the wavelength where the absorbance is the highest? Yes?
It's like the chip absorbs one color, it's not the.
If it absorbs one color the most, it transmits what? It transmits the opposite. So it would transmit the least. Why does that make it good? Yes?
This is a curve graph, so it's like the absorbance is not so high.
Yeah?
It'll be on the very left, and that'll be the number will be forgotten.
Okay. I'm not quite sure what you mean.
Okay, so the absorbance, right?
Yeah.
The absorbance is
Yep.
the lower the transmittance is.
Yes.
And the transmittance is like what's the graph called again? Where's curve?
Is this the one where you have absorbance and transmittance and it goes like this?
Yeah.
Yeah?
Exactly.
Is that what you're referring to?
Yeah.
Yeah. Okay. So that's not quite what we're getting at. Okay. What we're getting at is when you've actually put your sample in and you change the wavelength. This is the wavelength knob. Okay. So you change the wavelength. Your sample goes in here. You start at one wavelength, got your sample in there. You measure the absorbance and then you change the wavelength and your sample is it just stays in there. Okay. And you measure its absorbance and you'll get a plot that looks maybe something like that. Yes? This right here is the maximum absorbance. Yes?
Wait, can I click answer?
Yeah?
It's because if it like decreases, you'll still be able to see the number, because if it gets too low, then
Yeah, you want to choose the one where it has the highest absorbance, because then, even if you had a lower concentration, this one is a higher concentration. If you did that same plot with a lower concentration, it would look like that. Yeah? And if you did it at an even lower concentration, I didn't do a very good job there. Yeah.
why would the second peak be the highest one?
Oh, it shouldn't be. It's because I can't draw. Sorry. It's because I cannot draw.
Like the black graph?
Oh, it doesn't matter. It could be a higher one. It could be higher. It could be lower. I'm just making one up.
Wait, so higher concentration.
A higher concentration is always going to have a higher absorbance.
Okay.
So this is our higher concentration, the black line. The blue line is a lower concentration, and then our red line is the lowest concentration. Okay?
So it depends on what the graph looks like, or so like, because we thought like if it has the max absorbance, concentration would be max there as well, right?
No, because what we're changing in this experiment as we plot these points, what we're changing is the wavelength. The concentration is staying the same throughout the whole black line. Concentration is all the same.
What?
For the black line. Now, if you go to the blue line, that's a different concentration. Yes? But it's lower, but it's all the same. It's all blue concentration, okay? So it's all like 0.5 molar. Let's say this is 1 molar. And then the blue line would be 0.5 molar. And then the lowest concentration may be 0.1 molar. Yeah? And so you're going to get a better result with that lowest concentration if you choose the highest peak. Because if you choose something down here, this red line becomes virtually unreadable. Yes? Pardon me? Why is it unreadable? Just because it's really hard to distinguish it from zero. The machine doesn't have that level of sensitivity. Does that make sense? So if you were using this ruler, okay? If you were using this ruler, would it be easier to measure something that is 30 centimeters long, or would it be easier to measure something that is 0.01 millimeters long?
30.
Right? Because this measuring instrument does better with bigger numbers. This measuring instrument does better with bigger numbers. You'll be able to make more distinction between.
But I could get the bigger numbers, you will need like lower concentration.
No, to get bigger numbers, okay, so here's the deal. To get bigger numbers, you want to choose the maximum absorbance wavelength.
Okay.
That's it. That's it.
Oh, so like either there's more absorption or there's more transmit. So
Yeah.
You can tell it's like an obvious difference.
Yeah.
Oh.
Yeah. So, God damn it. Sorry. So let's just focus in on two areas of that graph. I'm going to give myself a little more room here. Why will you not move sideways for me? Oh, for God's sake. Okay, here. There we go. All right. I'm just going to make it one peak. No two peaks. We're just going to make it easy. Okay? No three lines, just one line. Okay. Let's say that this absorbance is, I don't know, 1,000. Okay? That means that if I have, and this is 1 molar, this is 0.5 molar. Let's say that this absorbance here would be, because it's half, that's going to be 500. Yeah? But if we're measuring down at this wavelength, good Lord, what would those numbers be? Maybe that's, I don't know, 10 and 20? Yeah? So the difference in absorbance, if this wavelength here is, I don't know, 400, and this one is, I don't know, 520. If I now start looking at different concentration samples, and let's say now I go to 0.1. This now is at virtually 0, right? The black line is now at 0 absorbance, whereas this one is at 20 absorbance. And I might be able to get another reading at 10 and another reading at 5, but if I'm here, everything is crammed in here. It's like all my measurements are being read on this part of the ruler. If I'm using this area of the graph, if I'm using 400 nanometers, it's like I'm trying to measure everything with this part of the ruler right here. Why would I not use this part of the ruler, right? Yes?
So we're using the maximal absorbance from like the concentration.
Yes. So what we're going to do is we're going to take different concentrations now. So experiment number 1, you take a nice healthy concentration and you plot the points at all the various wavelengths and you get this curve and you say, aha, 520 has the most absorbance. Yes? Then, so this is part 1. Part 2, part 2 is going to be all at 520 nanometers. Yeah? And then what you're going to do is you're going to have concentration versus absorbance. Okay? And you'll be able to get a plot like this. Yes?
Why do we need to know the best wavelength for lower concentrations when we have the data, the spectrometry data, this compound?
Because later on you're going to be measuring at lower concentrations, right? Like say you took your reaction mixture, right? Let's say we started with here's my reaction mixture and it's got lots of blue particles in it to start with. Yes?
Yeah.
So it's absorbing really nicely at orange.
Yeah.
Okay? So I want to shine orange light through it. Okay? Do I have an orange pen? Orange, there we go. Okay. Well, that's not orange, but whatever. Anyway, the light shines at it, a lot gets absorbed. As time goes on, because this is a reaction taking place, the blue stuff is getting used up. So now there is less blue stuff. So the absorbance will be smaller. Yeah? And eventually, there's going to be very little left. Yeah? So let's say that my absorbance here was 1,000. Let's say my absorbance here was 500. And my absorbance here is, I don't know, 25. Okay? This is using what we call the lambda max, which is that highest absorbance wavelength.
Orange light.
Yeah. Now, let's say I choose a low absorbance wavelength instead. The number is going to be lower. Yeah. So if we use a low absorbance wavelength, my absorbance will be, I don't know, maybe 10, 5, 2.5. And then if I use an even lower absorbance wavelength, 1.5, 0.25. Do you see how these start to become less readable? Right? And if I get into an even lower absorbance wavelength, my machine is eventually going to read 0, 0, 0 all the way across because it's like not absorbing very much light. And then I got useless data. So by choosing the wavelength that absorbs the most, you're going to continue to get data for the longest time as a species decreases in concentration. Yes?
Because it's like force on there, like you can see that it's like a problem thing. Yeah.
Okay, so here's the thing. That initial peak, that's just part one of the experiment. You're just saying, I want to choose this wavelength. This right here, this is my lambda max.
Okay.
We do that, and then we don't care about this graph anymore. This graph goes away. Bye-bye. Yes? That graph goes away. And now I'm going to graph this data. And this data here is going to look like this. So I'm going to have, this is all going to be at 560 nanometers. And I'm starting with a high absorbance, yes? And it's decreasing over time. Right? This is T1, T2, T3. So I start with a lot of the blue stuff. The blue stuff reacts. It gets used up in the reaction. So I have less of the blue stuff.
So when you like put it in the thing, is the reaction like occurring?
The reaction is occurring in the machine.
Okay.
Yes. Yes.
So then as time goes on, like yeah, sort of.
As time goes on, the absorbance drops. And in fact, it wouldn't look like this. It wouldn't be a straight line. It would be like this. Yeah. Yeah.
So this experiment is like to see how fast the mixture happens.
This would be a reaction rate experiment here. Okay? Yeah. So over time, you would have like a decreasing absorbance. But it would we would do it all at 560 nanometers. If you were to choose a lower, so this is at 560 nanometers. That's the peak. This is our lambda max. But if we were to choose something other than the lambda max, let's say we chose, I don't know, 220 nanometers, and it doesn't even absorb there. Okay, here's my absorbance versus time. Whoa, where'd it go? Is that good data? That's shitty data, yeah? No good, bad. And that's because even at high concentrations, it's not absorbing that much. Yeah? So you can get better data if you pick the one where it absorbs better. How are we feeling about that? Better? Okay. I love that you guys are asking questions about it though and like getting involved in the discussion because that means you're getting clarity. Yes. Yes. What's up?
I cannot hear it.
Does wavelength increase with time? No, because what we've done is we have set that machine. This machine, we set the wavelength that says 560, and it just shines that 560 degree, that 560 nanometer light. So wavelength does not change. Why is it going down? Okay, because in this, a reaction is occurring, a reaction that uses up blue stuff. That's what's happening here. Time is progressing and the reaction is using up the blue stuff. You need to speak louder if you sit at the back of the room. concentration is decreasing over time because the reaction is using up steps. So our absorbance is decreasing because the concentration is decreasing over time. Yes? When you shine the light, it's not that the light is causing the reaction. I mean, the reaction would happen whether it was here or whether I put it in the machine. But when you shine the light through it, as the amount of blue stuff decreases, more and more light will get through. Okay, so the transmittance will get greater and greater. The absorbance will get smaller and smaller. That make sense? The concentration is decreasing. So we could put absorbance here. We could also put concentration here because concentration is proportional to the absorbance, or rather we should say the absorbance is proportional to the concentration. The higher the absorbance, the higher the concentration. The lower the concentration, the lower the absorbance.
So you basically just like switch it like now.
Yeah. Okay. Not quite, but and that's why you have your formula. Absorbance equals that one. Yes. And so that's why absorbance is proportional to the concentration. But the nice thing is, blue substance is always going to have the same molar absorptivity. Yeah? The path length is always going to be the same because you will always have, let me go grab one. You will always have the same size. They call this a cuvette. Okay, and I don't want to touch it with my fingers because you would normally do this with gloves, but I'm just going to use the little tissue that's here. It just looks like a test tube, but it's better glass. The light passes through it really well. Okay, so it's going to be, the path length is going to be the same. It's always going to be 1 centimeter for this. This is 1 centimeter across. Is this becoming less mysterious? Yeah. Okay. Don't worry, this is not the last we're going to hear of it either. Okay. Yes? This would just be a reaction rates experiment. Okay, you would be finding a reaction rate, but you can do things often in first year university. All they'll do is they'll get you to like plot, find your lambda max, find your wavelength of highest absorbance, and then they'll get you to plot a concentration curve. So you'll make up a 1 molar solution and a 0.5 molar solution, a 0.2 molar solution, and a 0.1 molar solution, and you'll toss them each in, you'll measure the wavelength, and you'll read the absorbance. Okay? And that is going to allow you to actually figure out what the molar absorptivity constant is. But we'll talk about that later. Okay? All right. So I don't know that we need to watch this guy's video. Which wavelength would you choose in this experiment? Like, let's say this was our absorption spectrum. Which wavelength would you choose? Well, it doesn't have a number, but it would be the highest peak. That is our lambda max. Choose me. All right, and on the next page, it basically just says that. Choose me. And this next one, this next graph is just, it just shows what the transmittance spectrum would look like. You can see it's the opposite, it goes the other way. Right, there's our absorbance. The transmittance is basically upside down. As the absorbance gets smaller, the transmittance gets bigger and vice versa. Absorbance and transmittance, they're mirror images of each other. Minimum transmission is the same as lambda max. I don't know why I got excited about this. There we go. There's a few exercises. We're not going to do those right now. Okay, what did I do last year? Let's find out.
I want to stay on track.
1.7C. Okay, went over. First video, 1.7D. Okay, we're going to go to 1.7D. And that is on page 68. So like we were talking about, you can use the spectrophotometer to do rate experiments, but you can also, like, let's say you have an unknown sample. Actually, you know what? The video does a better job of it than I do. So let's take a look at the little video. Okay. Okay, so they will have made up these solutions. Someone will be like, okay, I'm going to make up 0.5 molar. I take 0.5 moles and I stick it in a liter of water, and then I make dilutions of it. So I get all of these different concentrations. What would you estimate that concentration is? 0.3? Sure. Okay. Looks kind of like 0.3. His picture probably looks better than ours does, and you can tell the color better. We're really ballparking it, okay? So path length is sometimes represented by the letter B rather than the letter L for length. I don't know why, but I think AP uses L, so we're going to go with that. I think they do anyway. Ooh, we should check. Let's see what they use, because this is on our data booklet, our AP equations, and we go to, let's see, solutions. There we go. Yeah, they do use B. Okay, so on your equation sheet, on page 1 of the equation sheet, we have absorbance. And you'll notice that it defines terms over here. So this is in your data booklet. We have A equals EBC, and it tells you over here, A is the absorbance, E is the molar absorptivity, B is the path length, and C is the concentration. Okie dokie? So it is in there. You do not need to memorize that formula. So you're putting them each in individually.
Tube, right?
Pardon me?
Tube.
Into the tube, yeah. What?
So the like the tube that you showed us.
Yeah, the cuvette.
But the concentration.
Yeah, so the like each of these, let's just pretend these are all individual cuvettes. So you would have separate ones, and you just make sure you clean them off every time. Okay, and then you put it in and you measure it.
How does it measure it?
How does it measure it? Let's go back here. Yeah, let's go to here. Let's go to, no, that one. Okay, so basically what's happening here, now that I've scribbled all over this, we have our light source, yes? And we select maybe yellow light, yes? And we know the intensity of that light that goes in, yeah? Now it passes through the sample, some of it gets absorbed, and then it hits a detector, okay? So there's a thing that measures the amount of light that is hitting it. And you can compare that to the original intensity of the light. Yeah? And then the machine spits out a number. Is good? Cool. Yeah.
With the cobalt mixture, it should be, the color should be green.
Yeah, probably. Yeah, because it's red, so it would be green. Yeah. I hope that's within the green range. Hopefully he did his math right. So this is the second thing you could do as part 2 of an experiment. And the one we were talking about before, part 1, we found our lambda max, yeah? And then in part 2, we were graphing, the absorbance versus time. Yes?
Oh, and why does it say like -0%?
Because maybe technically it should have a y-intercept of 0, but, the math didn't math that way because data isn't perfect. Yeah? Right? And we got 0.47. So lo and behold, it is between 0.3 and 0.4 molar. Yes?
So for the other show like these like, is that like always an error?
It will always be approximately linear. What'll happen is as you hit sort of the ends of the curve, it doesn't extrapolate well. Okay, so really you would only use a graph like this, the absorbance versus concentration. You would only interpolate rather than extrapolate. So you would try and hit within the known concentrations rather than outside, because it does tend to get a little off at some points. Yes?
I think probably the molar, they don't know what's the
Oh yeah, they don't know what this one is, but they do know this is their unknown, right? And this is their known samples, okay? And you know it's going to fall in between 0.3 and 0.4. So let's figure out exactly what it is by using our graph. Oh, you know it's cobalt. You know it's cobalt. You just don't know its concentration.
Oh.
Yeah? So this might be like, I don't know, let's say they were looking for a toxic substance, right, in a little sample of something. So they would take it and that's why they would choose that wavelength, because that particular compound absorbs really well at that wavelength. Yeah? Is good. Yeah, you can read off the graph. Or if you have found your equation, the y equals mx plus b, you can actually do the math. Is my clock fast? I thought it said 19. Okay, my clock is slow. So your homework is the exercises in 1.7b, and you're going to do 1.7c, which is a little activity. So 1.7b and 1.7c. Huh? It'll be posted on Teams.
Like it's always in the house.
Yeah.
Like what she said, I'm going to engineering. My physics. And I really care that I draw. happens when I take it online.
No, I personally dropped it and takes out.
So I was wondering if it would be a bad idea to take it as a section. It depends. Like if you're.
Okay, well, I got it.
I know, right?
Thank you.
You're welcome.